Today we will do a lab on optics. Optics is the study of light. So obviously one has to ask the question, what is light? Do you know what light is? Well, I don't think we have enough time to discuss that question, and therefore we are now going to say light is a form of electromagnetic radiations. Now, what do you know of radiations? We talked about that in a class on thermodynamics, that objects emit radiation at all temperatures. As the temperature of the object increases, the wavelength of the most prominent radiation will decrease. The wavelength decreases means the frequency increases. The energy of a radiation is proportional to its frequency. So as the frequency increases, the energy increases. You are familiar with that. Now, I have a filament of a bulb which is emitting radiation. Now, when the temperature is not so hot, when the filament is not so hot, the most prominent radiation that comes out of it now is infrared, is in the red region. You can see the filament is almost red. Now, if I increase the temperature, see what happens. The most prominent radiation, the wavelength become smaller, and now most of the radiation is in the visible region. The temperature of the filament now is over 4,000, about 5,000 Kelvin. Now, visible light is a combination of thousands of different waves. We got red, that is one wavelength, green, blue, violet. You see all these colors. How many colors are there in white light? There are about 3,000 different colors. That means there are about 3,000 different wavelengths that make up what is called the white light. What we call the red color is a combination of very many wavelengths that are the longest in visible light. As the wavelength becomes shorter, you see yellow, orange, green, blue, purple, violet. Now, violet is the shortest of all the waves in visible light. That means violet is the most energetic. So the visible light that we see, we call the white light, is a combination of thousands of different colors. And all these colors in vacuum, or for all practical purposes in the air, travels with the same speed. We represent the speed of light by the letter c, the lowercase c. And the speed of light in vacuum is 3 times 10 to the power of 8 meter per second. That means all these different waves of different wavelengths will travel with this speed in vacuum. But if you now allow these waves to enter from air into, say, glass, what happens is their speed will suddenly change. Each of these waves will undergo a change in speed. Now, the change in speed suffered by each of these colors will be different. Why? Because the energy value associated with each wave is different. If a wave is very high energy wave, that will undergo much more deviation than if the wave is not so much energetic. It is like if you go on a bicycle on a very level road and all of a sudden you come to a dirt road. Now your speed is going to change. If you are traveling very fast on the good road, you will be thrown away when you move into the dirt road. The deviation you suffer will be much greater if your speed is, if you carry a lot of energy. In the same way, violet, which is the most energetic, will suffer more deviation than red. So since I don't have a violet pen, I have only up to blue. So as blue enters the glass, it will go like this. It will not be going directly, but it will suffer a deviation. Now green will go like this, and red will go like this. In other words, red suffers the least deviation and purple or violet will suffer the most deviation. Now, the deviation suffered by a ray of light, as it enters from one transparent medium into another, is called refraction. So refraction is the process of a light ray as it enters from one transparent medium into another, it suffers a deviation in its path. And that process is called refraction. Now, the ability of a transparent medium to bend light is represented by a quantity called refractive index. And we generally represent that by the lowercase n. And what is the definition of refractive index? Refractive index is defined like this: n equal to speed of light in vacuum. Well, speed of light in vacuum we represent by c. C stands for the speed of light in vacuum, divided by speed of light in that medium. Well, that is the definition of the refractive index of a medium. Now, suppose we say n equal to 1.5. Well, what that means is, if the speed of light in vacuum is 3 times 10 to the power of 8, then the speed of light in a medium of refractive index 1.5 will be 2 times 10 to the power of 8 meter per second. Well, in today's lab, we will make use of the property of refraction of light. Here I have a collection of light rays, as you can see. If I allow this, say, one light ray to pass through a prism, now look at this, what happened to that? This light ray, as it enters the prism and comes out, look at the deviation it has suffered. And each color, if you watch the colors here, now which of the colors has deviated more? Well, that's the red end. That's the red, yellow, blue, purple. Now, the deviation depends on the wavelength. So a triangular prism produces this kind of deviation. Now, I want you to watch when I use two prisms. Tell me if the light ray bends towards, if this is the base of the prism, what I'm showing here. You can see the bending has happened towards the base. If I now use another prism in a similar way, you can see the net result is a convergence. So a beam of light that is falling on the two prism system gets converged on the other side. Now, this is the principle of construction of what we called a lens. If you now watch what I'm holding here, this is a lens, and you can see you can break it into two prisms at the middle. One will be one prism and the other prism. The bases are facing. Now watch what happens when I allow this collection of ray pass through this lens. What does the lens do? The lens converges the beam. Now let me see if I can move the camera so that you can see the complete convergence. Okay, there you have all those rays are converging to a point. Now this kind of a lens is called a convergent lens or a convex lens. So a convex lens, what does it do? A collection of light rays falling on it will be all converged to one point on the other side of the lens. On the other hand, now here we have the prisms placed base touching each other. On the other hand, if you place the prisms so that the vertices are touching like this, look what this has done now. Now what this has done is it has produced a divergence. It has diverged the beam away, and we can produce a lens using that. Now look at this lens. This lens also makes use of two prisms, but they are not the bases facing, but the vertices are facing. Now look what this does to that collection of rays. It produces divergence. So this kind of a lens is called a diverging lens or a concave lens. In today's lab, you will work with convex lenses. This is a convex lens. In fact, you will be using two convex lenses. Now, I can draw a convex lens like this. Let's talk about some of the important terms that we use in connection with a convex lens. One term that we will be using is, of course, the center of the lens. An axis that passes through the center of the lens, a horizontal axis that passes through the center of the lens, is called the principal axis of the lens. The principal axis. So a lens has a principal axis. What happens when a number of light rays falls on a lens? I'm going to draw some light rays. Now here is a light ray that is parallel to the principal axis. Another light ray. I have a number of light rays that are parallel to the principal axis. Now after passing through the lens, where will they go? Remember, this lens is a converging lens, a convex lens. So after passing through the lens, they will all converge to a point on the other side of the lens. Each of this ray will pass through that point. And this point is called the principal focus of the lens, the principal focus. A lens has a principal focus, and we generally represent that by the uppercase F. And if you now measure the distance from the center of the lens to the principal focus, this distance is called the focal length of the lens. The focal length of the lens. And the focal length is represented by the lowercase f. We represent the focal length by the lowercase f. Now don't confuse between the uppercase F, that is a point. That is the principal focus. Lowercase f is a length. It is a distance from the center of the lens to the principal focus. And very often you know that you wear lenses for correcting your vision. And when you go to the optician, he will prescribe you a lens, and it is the power of the lens that is used there. What is the power of a lens? Power of a lens is the reciprocal of the focal length in meters. You measure the focal length in meters and take the reciprocal of that. That is the power of the lens. For example, if the focal length is 20 centimeter, that is 0.2 meter, then the power of that lens is 1 over 0.2, that is 5 diopter. The unit of the power is called a diopter. So a lens has a focal length which determines its power. The most important thing about a lens is that a lens forms images of objects. And in today's lab, we will study the images formed by lenses. Here I have a lighted object. That's actually a bulb, and that's the object. And you see the filament of the bulb is the object. And this is the lens, and you see the image of the filament. If you notice, the filament is actually like it's an upside down U, the object. But when the image comes, it is a U. That means the image is actually upside down. So, now look at my pen. I'm placing the pen in front of the object. And look at the image that it has produced. The image is upside down. So a lens can produce an image. And in this lab, we will be using distances. Look at now, the distance measured from the position of the object where I'm pointing. I have actually put a line there. This is the position of the object. Measured to the center of the lens is called the object distance. And the distance measured from the lens to the image is called the image distance. So we will work with object distance and image distance. Alright, now before we come and do the lab, let me discuss a little more on the lenses. Let me show you how we can construct images on a convex lens, on a converging lens. Now this is my lens, and when you draw the diagram, you need to mark now here is the principal focus, and the principal focus is represented by the uppercase F. So it has a focus on the right and also on the left, and also mark the distance called 2 times F, twice the focal length of the lens. So these are important points. What do you call this line? That is the principal axis. Now tell me, if I take a light ray that is parallel to the principal axis. Now here I have a little boy. A light ray starting from his head and falling on the lens. Where will it go? It will go through the principal focus on the other side. There you are. So this ray will, after passing through the lens, will go through the principal focus. Now, suppose I take a ray that passes through the principal focus. After it passes through the principal focus, where will it go? It will go parallel to the principal axis. Now, these two light rays are meeting here. That means the head of the boy will appear over here. Now, that will be the head of the boy, and you can see the image like this. The image will be upside down. This is how we construct images. We only need 2 light rays to construct the image. And now I told you the distance of the object from the lens is represented by the uppercase U. The uppercase U is for the object distance. Don't confuse there. U stands for the object distance, distance of the object from the lens. And the distance measured from the lens to the image, the position of the image, is the image distance. We will use the uppercase V for that. And now, in our lab today, we will measure these 2 distances and use them to obtain the focal length. And that equation is 1 over U plus 1 over V equal to 1 over F, where the lowercase f, the focal length, is represented by the lowercase f. The distance of the principal focus from the center of the lens is called the focal length, and we will represent it by the lowercase f. 1 over U plus 1 over V equal to 1 over F. If you solve this equation for F, you get F equal to U times V divided by U plus V. So, what all you need to do is do the experiment for different values of U and V and draw a graph of U times V on the vertical axis and U plus V on the horizontal axis. The slope of that graph will be a measure of the focal length. That is one way to obtain the focal length. Another way is, I want you to pay attention to understand that second method. If you draw a graph of U on the vertical axis and V on the horizontal axis, what kind of graph will you get? Well, the graph you will get will be something like this. And I would like you to draw this graph. Draw a graph of U on the vertical axis and V on the horizontal axis. And once you have this graph, draw a line making 45 degrees with the x-axis. Alright? Now that line will cut the graph at the point P. Now what is the characteristic of that point? If you look at this now, if this is the origin and if you draw a perpendicular from P to cut the x-axis at A, you notice that OAP is an isosceles right triangle where this OA is V and this PA is U. Is that right? And that means because this is isosceles, the value of V and U will be the same. So point P is such that at point P U will be equal to V. Alright, let's write down the lens equation. The lens equation is 1 over U plus 1 over V equal to 1 over F. And what is the specialty of point P? At point P, U equal to V. So, if I replace this V by U, I will get 1 over U plus 1 over U equal to 1 over F. Now, this is valid only at P. At P, I can replace V by U. Now, 1 over U plus 1 over U is 2 over U. Is that right? 2 over U equal to 1 over F, or it tells me that U equal to 2F. Now, Once you locate the point P by drawing a 45 degrees line with the x-axis, if you now draw a perpendicular down, measure that distance OA, and that, or measure that distance PA, well, that P corresponds to this point. And this value of U will be 2 times the focal length. Similarly, this value of V will be 2 times the focal length. So, you can determine the focal length F by 2 methods, by drawing 2 different graphs. And I want you to do this for 2 different lenses. Okay. However, I want you to do the experiment for another method, a third method for measuring the focal length. Alright, I'm going to take this off. You got to take a special note of this particular graph. Start by taking a look at the experimental arrangement. This is the lighted object, and the position of that is marked by a dark line on top. You can see it. This is the lens, and I have tried to mark the position of the lens with a white strip on top. If you look carefully, you can see it. The distance between the object and the lens, which is the uppercase U, is measured between those 2 lines. The distance between the lens and the image is measured between the center of the image and the center of the lens. Now, in order to measure the distances, we need the conversion factor. But in this case, you need a conversion factor for measuring the object distance, another conversion factor for measuring the image distance. Alright, I'm now going to ask you to measure the length of this ruler 2 times, and to do that, I'm going to turn on the light first. This is the 30 centimeter ruler. I want you to measure the length of this from this point to this point and calculate the conversion factor as 30 centimeter divided by your measured distance. I'm going to give you 10 seconds to do that. Right. This conversion factor will be used only for the object distance. In order to calculate the image distance, I want you to measure this length. Alright, measure the length of this 30 centimeter ruler from here to here and work out the second conversion factor, 30 centimeter divided by this length. So remember, when you measure your object distance, measure the distance on the computer screen and multiply it with the first conversion factor. You measure the image distance on the computer screen and multiply it with the second conversion factor. Alright, I hope you got that length measured. The distance from this point to this point. Calculate and record both conversion factors. Okay. In the experiment, I will keep the lens at a certain distance from the object and I will ask you to measure the object distance. Then I will move the screen so that the image will go from well-defined to blurred. You need to stop the video when you see the image the clearest. Alright? At a position where the image is clear, stop the video and then measure the image distance. Alright, let's start with the first object distance. Measure this object distance. I don't need to give you too much time. What I would like you to do is, you stop the video for the image and then measure the object distance and the image distance. Alright, watch for the image and stop the video when it is clear. I am moving the screen and look for the clearest image. Okay. Stop the video when the image is clear. Alright, I think you had a very clear position. Alright, and now stop the video and measure the object distance and the image distance. Okay, now I'm going to move the object so that you have a new object distance. There you are. You got a new object distance, and I'm going to move the screen so that you can now measure the image distance. Alright, look for clarity of the image. When the image is very clear, you stop the video. You see. Now let me tell you how you look for the image. In addition to the filament image, you see that center part. When you see that central part clear, that is where you have a clear image. So stop it when you can actually see that, like a little hook. When you can see that hook properly, that is where the image is clear. Stop the video when that becomes clear. There you are. Okay, stop the video, measure the object distance and the image distance. Now this is the second trial for the first lens. Alright, let's now do a third object distance. I'm now going to change the distance, the object distance. That's a new object distance. And stop the video when you see the image very clear. And move it forward and backward. You need to stop it when the image is the clearest. Alright, stop the video and measure the object distance and the image distance. Always remember, multiply the object distance by the first conversion factor, the image distance by the second conversion factor. I'm going to increase the object distance again. That's the new object distance. This is the fourth trial. And look for the clearest image you can get. Alright, stop the video where the image is the clearest and measure the object distance and the image distance. I will now increase the object distance again. That's the new object distance. And let's measure the image distance. Well, you can stop it there and measure the object distance and the image distance. Alright, I think we did 5 trials now. We will do one more, a 6th trial, the new object distance, and see where we can find the image clear. I will help you with this. I'm going to stop it where that image is clear. Well, that is the clearest image. So stop it there, measure the object distance and the image distance. We will now work with the second lens. The conversion factor for the object distance, you can use the same as for the first one. But the conversion factor for the image distance, I would like you to measure again one more time. So measure the distance from one end to the other of this ruler. Then work out the new conversion factor for the image distance, because that distance is coming closer and closer. As the angle of the camera changes, that distance needs to be recalculated. So for the object distance, you can use the same conversion factor you used for the first lens. For the image distance, if you haven't measured this, measure it again and work out the conversion factor. Okay. Well, I have the first object distance, and stop the video when you think the image is very clear. Alright. There you are. Okay. Stop the video there and measure the object distance and the image distance. I will continue because you will be stopping the video to take the measurements. We have now a second object distance, and look for the clear image where you can stop the video. Now look inside that hook-like structure and see whether you can see that clearly. That is when the image becomes clear. Alright. So stop the video when you can see it clearly and measure the object distance and the image distance. Alright, we now change the object distance to a new distance, a new object distance, a third value, and stop the video when you have the image clear. Okay. Now measure the object, stop the video and measure the object distance and the image distance. Let's now take a fourth value, a fourth object distance. This is the fourth object distance, and look for the corresponding image distance. Alright. Stop the video there and measure the object distance and the image distance. Remember, the object distance is multiplied by the first conversion factor, the image distance by the new conversion factor you worked out. The new object distance now, and find the corresponding image distance. Alright. Stop the video there and measure the image distance. It's not very different from the one you measured earlier. Okay. Last object distance, and let's find the corresponding image distance. Okay, stop the video there and measure the object distance and the image distance. We have now finished the first two parts of the experiment using the two lenses. Now we will use the two lenses once again to do the third part, and we will start by measuring the conversion factor. Alright, we will use this conversion factor for both lenses. So measure the distance from one end to the other of the ruler and work out a conversion factor. 30 centimeter divided by the measured value. Okay? Alright. In the third procedure, we will keep the object and the image distance called the uppercase D, measure that distance, and then we will keep the lens in between so that we've got a magnified image, and shift the lens, the position of the lens, so that you got a diminished clear image. There you have. And the distance through which the lens is shifted is the lowercase d. Alright, now how are you going to measure the lowercase d? Let's start by measuring, stop the video and measure the uppercase D, the distance between the object and the screen. Measure that distance, and once you are ready, I'm going to now obtain the first position of the lens. Alright. Now, the first position of the lens that gives you a clear image is this. Alright. Now, I'm going to indicate that by this ruler. Or maybe I will use my red pen. That's more visible for you. So this is the position of the lens that gives you the magnified image, and now let's obtain the diminished image. That's the position of the diminished image. Now the distance between the initial position and the final position is your lowercase d. Alright, stop the video and measure that. We've got the uppercase D and the lowercase d. That is our first trial. Okay? And now I'm going to increase the uppercase D by moving the screen backward. I have now a new uppercase D. Let's find the first position of the lens. To give there I have the first position of the lens that gives me a magnified image, and I'm going to indicate that by my red pen, and now obtain the diminished image position. Alright, stop the video now and measure the uppercase D, the distance between the screen and the object, and the lowercase d, the distance through which the lens is shifted. Okay, now I'm going to move the screen so that you got a new uppercase D. Alright, let's find the first position of the lens that gives you the clear image. That is this, and I'm going to indicate that by the position of my pen, and the diminished image position is there. So stop the video now and measure the uppercase D and the lowercase d. We will do only one more trial. Okay, I'm going to move the lens, the image back, the screen back, and look for the magnified image. and there I have the magnified image, and I will mark the position of that with my pen, and let's obtain the diminished clear image, and there it is. So measure the distance between the screen and the object, uppercase D, and the distance the lens is shifted, the lowercase d. Let's now do the same procedure for the next lens. Actually, this is the first lens we used for the first part. Alright? So don't confuse. The lens we have just used for the uppercase D and the lowercase d is the second lens. And now we're going to do the first lens. Okay. Now, to begin with, we need the conversion factor one more time. So I want you to measure that conversion factor. Here, I want you to measure the distance from one end of the ruler to the other and work out the conversion factor. Alright? Okay. I have now the object and the screen. I'm going to move the lens so that you got an enlarged clear image. There you are. And mark the position there of the lens. I have marked the position. And move it to get a diminished image. There I have the diminished image. Now, the distance through which the lens is shifted is the lowercase d. Stop the video and measure the uppercase D and the lowercase d. Okay. Now change the uppercase D to a new value, and this is the clear magnified image, and I'm going to mark the position there. And let's now obtain the diminished image. There you are. Now stop the video, measure the uppercase D and the lowercase d. I have now a new uppercase D, and let's find the first position of the lens. There I have the first position. I'm going to mark it with my red pen. There it is. And find the diminished image is there. Alright, stop the video and measure the uppercase D and the lowercase d. Remember to multiply it with the conversion factor. Now I have changed the screen so that we have a new uppercase D. Let's find the position of the lens for magnified clear image. There it is. Mark the position of the lens, and I'm going to mark it with my red pen. And find the diminished image, and there I have that. Stop the video and measure the uppercase D and the lowercase d. And finally, I have another uppercase D distance. Let's find the magnified image position. There it is. Isn't that a beautiful image? Yes. Mark the position and find the diminished image position, and it is there. Stop the video, measure the distance through which the lens is shifted. Now that's the center of the lens. You got to make a guess there, right? That's the center of the lens there. So measure the lowercase d and the uppercase d, and that's it. We've got the complete data set now. So for each lens you will have 3 graphs. What are the 3 graphs you will have? You will have a UV against U plus V graph. Then you will have a U against V graph. And what is the third graph you will have? A graph of uppercase d squared minus lowercase d squared against the uppercase d. The 3 graphs, each will give you a value of the focal length. Find the average for each lens. Alright? Okay, remember, we used the lens 1 and lens 2 for the first 2 parts, and the lens 2 I used for the first 2 parts was lens 1 for the third part. So keep that in mind. Okay? It's a good lab, and I want you to answer all the questions and complete the report. And if there is a question that you want help with, let me know and we will talk about it.